Hello everyone, here we are again. This time it's Chapter 8, titled Advanced TCP IP Network Design. In our last episode, you might recall we were talking about Classful IP Addressing, which included the three usable classes of Class A, Class B, and Class C, and we identified the fact that the first few bits identified the class, then that's followed by the network ID, which is followed by the host IDs. So the main thing that you want to recall from that is that IP addresses are divided into two segments, network ID and host ID. In this chapter we really don't worry too much about class ID because classes aren't used anymore. We now use classless addressing. The problem with classful addressing was it was very wasteful as far as the assignment of the IP ranges, and so a lot of companies got IP ranges that were more than what they needed, and so there was a lot of unused IPs out there that weren't available then to other organizations or other users. And so we've switched from the classful addressing scheme to a classless, but we still have the two major components of an IP address consisting of the network portion of the address and the host portion of the address. This slide basically reiterates what I was just telling you. Classful addresses are broken apart on octet boundaries. The first few bits of each segment address is used to denote the address class of the segment, and the class ID plus the network ID portions of the IP address are known as the network prefix, the network number, or the major network. When IP address classes were first established, networks were composed of relatively small numbers of relatively inexpensive computers. As time went on and the PC exploded into local area networks, the strict boundaries of the classful addressing address classes became very restrictive, and it forced an inefficient allocation of addresses. Class C address ranges has a limit of 254 hosts per segment, which sometimes is too small for a lot of organizations. Class B addresses had a limit of 65,534 hosts per subnet, which is much too large for many organizations. In fact, the IEEE, the organization that defines a lot of the lower layer, the physical and the data link layer specifications for networking, have basically stated that you should never have more than 1,024 hosts on a single segment. So as networks grew and needed to be divided or segmented in order to improve traffic flow, we had devices called routers that were developed, and they're designed to use or to join two separate networks or subnetworks, segments, together. Networks that are separated by the routers have to have a different network ID so that the router can distinguish between each of the networks. This accelerated then the depletion of IP addresses. Combined with that now your cell phone and fairly soon your microwave oven will most likely need an IP address. There's just so many devices that require IP addresses these days that also contributed to the demand for IP addresses. So we had this depletion by not assigning addresses correctly in the first place, by over-assigning ranges, and then we've got this demand by having more devices that require IP addresses. RFC 950 gave users a way to subnet or provide a third layer of organization or hierarchy between the existing network ID and the existing host ID. So we talked previously about how we divide an IP address into the network portion and the address or the host address portion, but now they're just saying that we're going to borrow bits from the host portion, and those bits are going to be the subnet portion. We haven't talked too much in this class yet about RFCs or request for comments. Just understand that the Internet Engineering Task Force, which you can go to their website at ietf.org, they're the organization that's really responsible for maintaining and overseeing the development of all the new technologies that are used on the internet. And the way that each new technology is recommended for use is through a document called Request for Comments, or RFC. So every time a new technology is designed, or a company wants to have the internet use it, or suggest that it becomes standardized as a component of the internet, they submit a document called an RFC, and then each of those documents gets assigned a number. So you'll see that all of the technologies that are used on the internet are defined by one RFC document or another. So in this case, subnetting, the very first versions of subnetting are defined in RFC document 950. Now, since the network IDs cannot be altered, the only choice is to borrow from the host bit. So we're back to talking about now creating that subnet portion of the IP address. So the network IDs are always locked in, because that's how the outside world finds your organization. And so you can't change that. You can't alter those bits. So say you were given a subnet mask of 255.255.0.0 by your telco or your ISP. Your mask will always have to begin with 255.255. You can't change that. So instead, what we do to create subnets is we borrow some of the bits from what's left over, which is, of course, the host portion of the IP address. These borrowed bits constitute the subnet portion of the address. A subnet mask, then, is what is used to identify which bits are used for the subnet ID. And that's not an absolutely accurate statement, in the sense that what you need to understand is that the subnet mask is the component that is used to define in an IP address which portion is the network and which portion is the host. So what will happen is you'll be adding to the original network address when you borrow from the host to create your subnet IDs. And so the subnet mask is going to be expanded, because what a mask does is it basically masks out the host portion. So what you're left with is the beginning, which is the network portion, and that's what gets compared by routers to see is the source address, and what is its network address. To find what its network address is, it could care less about the host portion, and so it has to figure out what the network portion of the address is, and then it uses that to compare to its routing tables to figure out what interface it's going to forward that message out of. And so the subnet mask is what actually defines in an IP address which portion is the network and which portion is the host. And so the subnet ID actually will become part of the network address. We'll be adding to the existing network address. Now, your author refers to this as the extended network prefix. So again, all we're doing is we're taking the original network portion of the IP address and we're adding to it. Let's take a look at the example, and I think I can explain it a little bit better that way. When you look at the graphic here, you've got the IP address of 128.210.49.213. The subnet mask that goes along with that IP address is 255.255.255. So we know that 255 is a sequence of 8 ones. And in fact, when you look at the graphic, they also convert the decimal values into the binary values there. So in this particular example, what they're saying is that the first 2 octets represent the whole network, and then the individual segments inside of the organization that make up the sub-networks of the larger organization's network, those are going to be the subnets. And so the first 2 octets of the network, the 3rd octet is used for the subnet, and then the remaining bits, the 4th octet, will be used for the host ID portion. So if you read the text here, it says the extended network prefix is the classful network prefix. So in other words, a class B address. Remember, the class B's start at 128 and go all the way up to 191, right? So this is if we were talking about classful addressing, this would be a class B address. Well, if you recall, a class B address, the first 2 octets represent the network value. The remaining 2 octets are the host portion. So the original subnet mask then was 255.255.0.0. So again, that represents the entire network for the organization. Now we're going to break it into smaller chunks, and so in order to do that, we need to borrow some of the host ID bits. So in this example, they've used the whole third octet for the subnet. So they borrowed 8 bits out of the host address portion. And so now, instead of being a /16, now it becomes a /24. And anytime you hear slash in a number or CIDR notation, which means the same thing, all they're indicating there, the 16 for instance, means the first 16 bits of the IP address are the portion that represent the network. The way you represent that in a subnet mask is you would have 16 contiguous ones. In other words, 8 ones in the first octet, 8 ones in the second octet for a total of 16 ones. Convert that to decimal, that's 255. We're now adding an additional 8 bits here, so now we've got a total of 24 bits that are being used to identify the network. So it's a combination of the large network, and then within that network, the sub-network where the device exists. So anytime you see a slash value, just understand that represents what the subnet mask looks like for that network. And anytime you have a subnet mask, the ones are always contiguous. You'll never see 110 and then some more ones. It'll always be a string of ones, and as soon as you see a 0, it'll be 0 all the way to the end. So there's no mix of ones and zeros. They don't alternate. It's always ones first. Wherever there's ones, that's the network portion. As soon as we have a 0, the rest will all be zeros, and then those zeros represent the host portion. So again, that's how the subnet mask is used to define the network portion and the host portion in an IP address. So here again, just getting into a little bit more detail as far as what we've just talked about. Class B, if we're using classful addressing, a class B would normally be a mask of 255.255.0.0. And again, they show that to you in binary. That's 16 ones followed by 16 zeros. First 2 octets of the network, second 2 octets of the host portion. And there's only one subnetwork. I mean, it is one network at that point. The bits that are left over, the zeros, the 16 zeros, means that you have the possibility of having 65,536 hosts on that network. The way you arrive at that value is, I always say, just look at the bits and take 2 to the power of the bits. In other words, we've got 16 zeros there. So let's raise 2 to the 16th power, and that tells us how many hosts we can have. Now 2 to the 16th power is actually 65,536, so you have to subtract 2 from that equation because you can't have an all zeros host and you can't have an all ones host. So you always subtract 2 out of the mass. So once you take 2 and you raise it to a power of, in this case, 16, you come up with 65,534. You just have to, for 536, sorry. You just have to remember to subtract 2, and that's the actual number of hosts then that you can have on that network. So then we actually break this down into chunks. We take the large network and we sub-network it. We break it down into a bunch of smaller segments. And so in order to do that, we had to take from some of those zeros. So in this third octet, again, we're adding ones now to the mask instead of the zeros that were there previously, because again, ones represent where the network is. So in the third octet now, because we've used all 8 ones, you can take 2 to the 8th power, and that tells you would have 256 subnets, but you can't have an all zeros subnet and you can't have an all ones subnet. So again, you always subtract 2 out of that equation as well. So it's 2 to the 8th power, 256 minus 2 means we can have 254 subnetworks. So just picture that as segments. Each individual segment now is its own network within this large network. On each segment, because of the way the math works, you have 8 bits left over for the hosts, the 8 zeros now at the end of the subnet mask. So the math there is the same, 2 to the 8th power, 256. Subtract 2 for the 2 scenarios we can't use, the 2 values that can't be assigned to hosts, zeros, and all ones. And so you have on each individual segment a maximum of 254 hosts that you can have on each one of those segments. So what you're seeing here is obviously there are limitations of this classful addressing that we've been talking about, and because getting back to that previous slide, the way that that would work is, as we said, we'd have 254 subnetworks, and you'd have 254 addresses, really, host addresses that could be used on each one of those networks. Well, what if you only had 10 devices on one subnetwork? Well, you've just wasted 244 addresses, right? So it's a very wasteful way of doing things, having both the classful addressing scheme as well as fixed length subnet masks, meaning the same subnet mask is used on all segments within the entire network. So what we're going to talk about here in a bit is we're going to talk about variable length subnet masks, where each subnetwork, each segment would have its own mask based on the number of hosts that we wanted to actually use on that particular segment. So just going through the bulleted items here, wasted addresses, only one subnet mask can be used for the network prefix. A shrinking pool of available IP4 addresses, because again we've got so many more devices that require IP version 4 addresses. Routing protocols, remember that's the way that the routers share their routing tables with each other. A route is through a routing protocol, and one of the first routing protocols, which was RIP, was unable to transmit subnet masks that are variable length. And even subnet masks that we've converted from classful addressing. In other words, RIP, if it saw that it was a Class B network, it would always assume that the mask was 255.255.0.0. Okay, so there was no way to do otherwise when we used the RIP protocol for exchanging routing tables between routers. So that was another limitation that we had with these fixed length subnet masks, is that the routing protocol would only support fixed length subnet masks and classful addressing. Some other limitations: routers, servers, workstations within a given network would all again have the same subnet mask. A fixed subnet mask implies a fixed subnet size for all subnets of a given network ID. Subnets must be sized to accommodate the largest required subnet within a given network ID. So if you had a segment that required, say, 1,024 hosts in the old way of doing things, then all segments would have to have 1,024 hosts, although again you may only be using 10 devices on that particular segment. So it obviously resulted in wasting a lot of host addresses that can't be used elsewhere. This slide then shows you an example of using variable length subnet masks, meaning that the mask length can be different on different subnets. So initially the organization has a Class A address, and its network address is 121.0.0.0.8, meaning that the mask is 255.0.0.0. Remember, 8 means there's 8 ones in the mask, and then the rest are all zeros, so that's 255.0.0.0. And indicating, of course, in the IP address that only the first octet represents the network, the rest is all used for the hosts. So we can now subnet that Class A into smaller chunks by adding bits into the mask, adding ones into the subnet mask, borrowing from the host portion. So if you're looking at the graphic there, you can see that in the row that says subnets, we've gone from a /8 now to a /16, meaning you now have 8 bits in the first octet and 8 bits in the second octet, which means that every value in the second octet will represent a different subnetwork. So you have the 121 network, and then the .1 subnet, the .2 subnet, the .3 subnet. Each one of those is a different segment then inside of the corporate network. Now we take those subnets and we further subnet them, but in the pink example, if we're looking at the third row down, the left-hand graphic there, we've got a /24, which means now we're going all the way into the third octet, and each different value would represent a different segment. So we're in network 121, subnet 1. See, all of those are in the second octet, use a value of 1. And then when we get to the third octet, 1, 2, 3, etc., all the way up to 253, 254, each one of those would be a different sub of that particular subnetwork, of the 121.1 subnetwork. Whereas on the right-hand side, in the gray box, you notice they're using a /19 there. So with 19, you've got the first 2 octets that are the network ID. That's accounting for 16 bits. And then we've got 3 bits left over in the third octet that are also representing in this case, the sub network of the subnet. And just won't go into the math quite yet, but the 3 bits means that your subnetworks are going to jump by 32s. So from the 121.253 subnet, we're going to further subnet it, in other words, break it down now into smaller chunks. And you'll have the .32 subnet, the .64 subnet, the .96, 128, 160, all the way up to 192. And now if you go down to the very bottom row there where it says the sub2 subnets, you'll see that for the left-hand subnet, because this is a hierarchical structure that we have now, on that 121.1.253 subnetwork, they've added some more bits into the mask, and now they're actually subdividing it so that, again, there's an additional 3 bits added there, right? Before we had 24 in the row above, now we're using 27. So again, we're jumping by 32s. So the sub2 subnets in the left-hand column there are 32, 64, 96, 128, 160, and 192. In the right-hand column, where we borrowed previously only 19 bits, we're using the 121.253.160 subnet, but now we're breaking it into additional jumps by adding 3 more bits. So now we're jumping by 4s, and so the subnetworks there are 164, 168, 172, 176, 180, and 184. So it was RFC 1009 that specifies how a single network ID can have different subnet masks, or in other words, variable length subnet masks among its subnets. And that is a hyperlink there. If you want to click on that RFC 1009 hyperlink, it'll actually take you to the actual document that defines the ability to use variable length subnet masks. This minimizes the wasted IP addresses that were forced by the single or fixed length subnet mask per network ID as defined by the original RFC 950. That's also a hyperlink if you want to see that original document. Both of those are on the IETF.org website. Now, in order for variable length subnet masks to work, the routers need to support that technology. So if you have an old enough router, it may not support variable length subnet masks. It may use the older RIP protocol. And remember, RIP didn't support variable length subnet masks. But as long as it supports some of the newer routing protocols such as OSPF and IS to IS, then you'd be okay. But if it only supports RIP and IGRP, then you would not be able to support variable length subnet masks. Now, RIP version 2 has added support for VLSM, so that one will work if your router supports RIP version 2. And you can see that technology too, RIP version 2, also has its own RFC 1388. So all routers supporting VLSM must support a longest match routing algorithm, and the implemented network topology must match the distribution of addresses and the definition of subnets. So just when you think you've got things figured out, and we've talked about subnetting, which is taking a larger network and breaking it down into smaller chunks, now we're going to go the other direction. We're going to talk about route aggregation with variable length subnet masks, and really all this is just the reverse of subnetting. If you think about routers on the internet, you wouldn't want the routers, your edge routers on your network and your ISP routers wouldn't want to be just overwhelmed with numerous network addresses in their addressing tables, in their routing tables. And so it's better if we can aggregate, in other words, combine a bunch of subnetwork addresses together, represent them with one network address, and just put that one network address as an entry into the routing table. Because you're going to use the same interface to get to that destination of the one address, and then once it gets to that destination, then they can be subdivided and redirected appropriately to the subnetworks that you need to get it to. So level 3 networks are subnetworks of level 2 networks, and so when you're looking at the graphic here, level 3 is at the very bottom of the graphic, and so those are the subnetworks of the level 2s, the one above them. And again, this is just the reverse. If you go back to the previous graphic here when we were taking it from the top down, we're just working from the top bottom up now. But so you can see we've got that 121.1.253, 32, 64, 96, 128, 160, 192 in the bottom left-hand box there. So all of those can be aggregated together as one address entry in a router's routing table as 121.1.253. Then, and the same is true for the right-hand one. I won't go through all the individual ones, but all those individual subnets on the right-hand side can be represented as the network that we see in the pink box right above the router 6. So then those networks, as we move up to the next router, is really just one value of, again, a collection of subnetworks which can be represented by a larger network scheme. And if you notice, we're moving the bits backwards now, right? Previously we're adding ones from the left to the right. We were borrowing into the host portion. Now what we're doing is we're backing them back out again. So we were at level 3, we had 24 bits and 19 bits being used in the subnet mask. Now as we move up to level 2, we're only using 16 bits in the mask, and then eventually we get up to level 1 there, and we're using only 8 bits in the mask. So it really is the same thing. It's just looking at it from a different perspective, looking at it from the bottom back up. And so the real point of all this is that the edge router, if we call router 1 our edge router for the network there, it's simply going to pass one network value to the ISP router, let's say, that it's attached to. It's going to say, put this entry in your routing table. Anytime anyone needs to get to 121.0.0.0, then you just point it my way. And so anything that comes to 121.0.0.0 is going to be received by router 1. Router 1 then is going to forward the information into its subnetworks, and then router 2 is going to subdivide it into the level 2s, and then each of the routers below that, 3 and 4 will forward it down, and 5 and 6 will subdivide it even more. So aggregation is just taking all of these small networks and just representing them as one larger network as a single entry in a router's routing table. So this aggregation process, what you'll hear it referred to a lot of times as classless inter-domain routing, or CIDR, CIDR, pronounced CIDR. And there's several documents that deal with this particular technology, RFC 1517, 1518, 1519, and 1520. You'll also hear CIDR referred to as supernetting. So subnetting, we're subdividing things. Supernetting, we're taking those subdivisions and aggregating them back into a smaller value. I mean, it's actually a bigger representation of IP addresses, right? It's a larger range that we're representing, but we're only using one network address to represent that larger range, and so that's also referred to as supernetting. So CIDR, or supernetted addresses, then are issued in blocks known as CIDR blocks. The first octet is meaningless in determining how many subnets or host IDs can be defined for a given CIDR block, because we're going to subnet at the lower levels. The only factor that determines the capacity of a CIDR block is the network prefix assigned by the Internet authorities when the CIDR block is issued. So in other words, when you as an organization go to your ISP and you're going to say, hey, we need to have X amount of IP addresses, well, it's going to be up to them to dictate exactly how many IP addresses you have, and that'll be determined by the subnet mask that they give you. So what they do is they assign you a network value, and then they'll give you a CIDR notation. So it'll always be network value / and then the CIDR value, which represents the number of ones that need to be in your host, your subnet mask, and the number of ones dictate what the subnet mask is going to be at the parent level at that edge router, and then you internally within your local area network can then use the host bits to subdivide that and break it into smaller segments, smaller subnets if you need to. So we're just reiterating that statement I've just made on the last slide here as far as implementation of CIDR. The network prefix issued by the Internet authorities. So Internet authorities really means ISPs at this point. You're not going directly to an Internet authority. You're going to an ISP, and they're the ones that are dictating the IP address range that your organization is going to use. Now they, depending on what level ISP they are, they may be dealing directly with various Internet authorities, but you as an organization will not be. So anyway, your ISP then is going to indicate the number of bits that are used for your major network ID. In other words, the network ID that represents your entire organization's network. And the bits are reserved. They cannot be used by the end user for subnet IDs or host IDs. So in other words, if they give you a CIDR value of a /19, you must have the first 19 bits in all of your subnet mask must be ones. You cannot back that up and make it smaller. You can't say, oh, I'll only use 16 ones and then I'll begin my host. It won't work that way. The outside world won't find your devices correctly if you attempt to do that. So you won't really cause any problems for anybody else but yourself if you don't adhere to that policy. And again, the point really is just whatever / value they give you, whatever CIDR value you give you, that's a fixed number of ones that you must use in all of your subnet masks. Again, you can subdivide by adding more ones into your subnet mask, but you can never reduce the amount of ones in the subnet mask less than what the CIDR value is that's assigned to you by your ISP. So the example here is if your CIDR block that was used for your network prefix is 18, that would imply the first 18 bits from the left to the right are reserved for your network ID. That leaves you 14 bits left over, right? Total of 32 bits. And so out of those 14 bits that are left over, then you can create subnetworks, and whatever's left over after you've subnetworked, then you've got the host portion. This table here is something that would be good reference. You can look it up to identify what the mask value is, the number of host addresses that it allows for, the number of bits that would be available for subnetting, and the equivalent number of classful networks, which really doesn't apply since you're not going to really concern yourself with classful networks anyway, unless at the lower levels maybe you had an older router that only supported RIP or something like that. So don't memorize this table, okay? Just use it as a reference point. I really always suggest that you learn the math and how it works, and that's, to me, has worked much easier. Then I don't even have to worry about trying to find the reference that will tell me this information. But let's just kind of take a look at it and go through it so that you'll understand what the information is. So the first column is the CIDR prefix length. So when we say /13, that means 13 bits in your subnet mask. So 13 bits means that the first 8 bits are used in the subnet mask as 8 ones, and the decimal equivalent of 8 ones is 255. So with that left over, or what is left over, is 5 more bits, so that if we translate 5 ones followed by 3 zeros, if you take 8 bits, remember each octet is 8 bits, so you've got 5 ones and then 3 zeros, that would be the value 248. So they're just saying that would be the mask then, 255.248.0.0, that your company would use on your edge router. You can further subdivide that if you need to. That would allow you then a total of 524,288 hosts. And you could figure that out by doing the math, because there's 3 bits left over in the second octet. Add that to the 16 bits left over in the last 2 octets, so you're talking about 19 bits. So raise 2 to the 19th power, subtract 2, and that is the number of host addresses that you would have available there. The number of bits for subnetting obviously is 19. The math there is, there's 32 bits in an IP address or a subnet mask. Subtract 13 from it, you got 19 left over. So it's not tough to figure this stuff out once you really understand the math and how it works. As you're probably aware, the solution to the fact that we're running out or have run out of IP version 4 addresses is IP version 6. If you look at this packet structure here, which is the IP version 6 header, you'll see that the addressing information now, instead of 32 bits as it was in IP version 4, is now 128 bits. And so that gives us, of course, many more nodes possible and addresses to be able to assign to those nodes. Let's go through the packet makeup here, the header makeup real quick. First of all, you have the version, so that's to identify the version of the packet, whether it's IP version 4 or 6. Of course, if this is an IP version 6 header, then obviously the version is going to be IP version 6. Priority of the packet indicates the class of service of the packet, basically whether it's time-sensitive information or like an email, data that is not sensitive to time and having to be forwarded in a basic priority or prioritized method. The flow label uniquely identifies the stream of data relative to other streams between the same source and destination. The payload length is exactly that, the length of the data that's inside of the packet. Next header indicates what type of header is contained in the payload of the IP packet. So this tells the destination node what protocols are encapsulated inside of the packet. The hop limit field corresponds to the time to live counter in IP version 4. It's an 8-bit, which means up to 255 hop counter, and it's just simply used to prevent the packet from wandering and looping around out there on an IP version 6 network forever. And then of course source address and a destination address remain the same, except that the difference is now we're using 128-bit addresses as opposed to 32-bit addresses. And then the checksum is the way that we check for reliability, make sure that the information was received correctly and can detect for errors. Here then are some of the advantages of IP version 6. It expands IP addresses to 128 bits. It eliminates packet fragmentation and the resulting processor overhead that occurs from having to fragment and put the packets back together again. It utilizes fixed length field headers, so no more variable length headers. And the packets can be set to be authenticated at their origin, and they can also be encrypted at the network layer. Switching gears now, we're going to take a look at the structure of the internet and how it's organized as far as connectivity options. The major carriers, which is your telcos, are all interconnected by internet exchange points. You'll also hear those referred to as network access points. In fact, sometimes you might even hear them referred to as the metropolitan area exchanges. They used to call them May West and May East back in the days of MCI, which of course MCI doesn't even exist anymore. So most predominantly you'll hear them referred to as Internet Exchange Points, or IXPs. So if you look at the diagram here, you'll see that we have the white clouds, which represent various organizational networks with their AS numbers, their autonomous system numbers, that are connected to ISPs. ISPs come in varying levels. You can see that the organization at the bottom is connected to a lower level ISP, which is then connected to a major level ISP, and the other organization there in connecting to the gray cloud is connected directly to a major ISP. And then both the major ISPs are connected to a major carrier, which is your telcos, and of course many times the telcos themselves are the major ISPs. Then between the major ISPs is where we have the internet exchange points. This map here has changed quite a bit since it was originally produced, but it shows you the original network access points that were defined, or IXPs that were defined for the internet. And so it is a little bit more updated in the sense that we have AT&T now listed here. Of course, they've always been a long distance carrier. Sprint listed here. We don't have Verizon listed here, which pretty much has taken over the MCI network. And so it's just showing you these different access points: Los Angeles, San Francisco, Seattle, Denver, Dallas, Chicago, Indianapolis, Atlanta, Miami, New York, and Boston are the major access points to the internet, and there have been some more that have been added, as I say, since this graphic was first developed. We're going to talk a little bit about routing now, specifically IP routing, and so you should be familiar with the fact that a router is the device that we use to route information from one network to another. As the bulleted point here says, routers serve as intelligent forwarding devices between subnets and networks. And the important thing to note here would be just to look at the network interfaces, the addresses that are assigned to these network interfaces for router A, and notice that they are attached to two separate networks, and the fact that the network address is different. So 165.32.1 is going to be the left-hand network, and 165.32.2 is going to be the right-hand network, and then the host itself, which is the network interface, and the router has been assigned 1 in both networks that it's attached to there. Then just notice too that the workstation addresses do use the same network address that the network interface card on the router does. That's very important that you understand that all devices on the same network always use the same network address. The router acts as what we call a gateway to each of its subnets. The router actually has a network interface card that participates in each subnet. You saw that in the previous graphic. So a routing device has multiple network interfaces, and each interface is attached to a different subnet. The router uses the subnet mask to determine the subnet IDs or network IDs of all traffic that the subnet mask is asked to process. And the way that a router determines which interface to use to forward a message to the appropriate destination is by its routing table. And so routers will exchange their routing table information with other routers so that those routers know which is the correct interface to be forwarding information for the networks that the router is attached to. So routes that are specific to networks can be entered into that routing table in two different ways: either statically, which means that a network administrator is manually entering that information into the routing table, or dynamically, which means that the routers are exchanging tables with each other based on what they're called route advertisements. And so as these route advertisements are sent by one router and received by other routers, then they, of course, the recipients are building their routes based on the information that they're receiving in these advertisements. Dynamic routing runs the risks of having one misbehaving router create a cascading negative impact on other routers. So if it has incorrect information that it's advertising out to other routers, then obviously that's going to be problematic as they pass that information along down the road to other routers within the network. In order for routers to be able to exchange their routing table information, they use what is called a routing protocol. And RIP, the Routing Information Protocol, is one of those protocols. Remember, we were talking about this particular routing protocol a little bit earlier on. We said it was limited because it did not support variable length subnet masks. So this is the header then that a RIP-based router would place on or in the front of the information being handed down to it from the upper layers, the UTP, or I mean the transport layer. In this case, they're showing a UDP header here. And so basically it has 8 bits for the command, 8 bits for the version, 16 bits which are reserved, 16 bits which are the family net 1, and then the net 1 address, which is 112 bits, number of hops to network 1, 32 bits, and so on and so forth. In other words, every time that we have an entry for a route, in a network address, then that's going to be an entry then in the information that's being put out there by the RIP protocol. There is a newer version of RIP version 2, and one of the big advantages is that it now supports the use of variable length subnet masks, which means it supports CIDR values. Another popular routing protocol is OSPF, Open Shortest Path First. It is what we call a linked state routing protocol, and it was developed to overcome some of RIP's shortcomings, such as the 15 hop limit. That was another limit of RIP, is that the routing advertisements can only go as far as 15 routers down the road. Also, the fact that RIP broadcast its entire table every 30 seconds was a drawback to RIP, and it was slow with regards to network convergence. That term network convergence means that all routers are up to date with regards to its knowledge of which routes are working and which routes are not. OSPF is, just like RIP, an interior gateway routing protocol, and it's used to share routing information inside of the autonomous system. So it's not an exterior routing protocol, it's an interior routing protocol. Here's a diagram showing the hierarchy of an OSPF area implementation, which has 4 tiers to it: the anonymous systems, the OSPF area, the network ID, and the subnet ID. So if you look closely there at the graphic, you'll see in the top left-hand corner is the gateway router. That's what we call the edge router, the one that is going to connect to the outside world. And so on its outside interface, it uses an EGP, an exterior gateway protocol. But then internally, and if you look closely, you'll see this router, the gateway router, has 2 internal interfaces there connected to 2 internal routers, and so it's using OSPF on those 2 interfaces and referring to the link or segment between itself and those 2 internal routers there as OSPF area 0. Then the 2 internal routers, the one on the top there, is using OSPF area 3 as its area designator, and it has 2 interfaces to 2 internal subnets, which are inside of a network that is ID'd as 1, and then inside of network ID 1 is where you have subnet ID 1 and subnet ID 2. So again, just kind of showing you the hierarchical structure of how OSPF works here. And if you look at the bottom, it's pretty much the same. The bottom router is connected to an OSPF area 1. It has a network ID 1 inside of it, and 2 subnets ID'd as 1 and 2. And then the same thing when there's a third router there in the bottom right, which they've identified that as OSPF area 2, and then inside of that, network ID 1, and again subnet 1 and subnet 2. One of the most frequently used external routing protocols is the Border Gateway Protocol, or BGP. And so that's the example we're seeing in this graphic here, specifically version BGP 4. So remember, external routing protocols are used to exchange table information with routers that are on the edge of organizational networks. So each organizational network is assigned an AS, an autonomous system number, and that essentially is the information then that's used in the routing tables of the exterior routing protocols. And here we can see a BGP4 protocol header. Basically has a marker made up of 128 bits, the length 16 bits, the type 8 bits, and then the data, which is a variable length of bits. So again, BGP4 is an exterior gateway protocol. It performs routing between multiple autonomous systems or domains and exchanges routing and reachability information with other BGP systems. The outside world, the AS is seen as a single entity. So each autonomous system, which is basically different organizations, they internally are going to be running their own interior gateway protocols independent of any of the other organizations or autonomous systems. So you might have one company running RIP inside, one company might be running OSPF inside, and that's really not going to affect the way that the border gateway protocol is working between the edge routers. Any network can talk to any other network via the internet, because regardless of what routing protocols they use on their networks and what they're using internally as far as their routing protocols, they're all going to be speaking the same language, BGP, externally. To finish up this chapter, we're going to take a look at some topologies that use LAN switching devices. And so in our first scenario here, what they're showing you is the fact that we have several different workstations all connected to a single LAN switch, and so they can all communicate with each other, and when one of those devices broadcasts, then it can send to all ports. So the big difference, remember, between a switch and a hub is that a hub is always broadcast. In other words, there's a message sent into a hub, it comes out all ports, whereas with a switch, the switch is dynamically identifying the pathway between the source and the destination, and only those two ports are communicating between those two devices, so that frees up all the other ports to be used by the remaining devices on the network. And so that's what this graphic is trying to demonstrate for you. But then when there is a device that needs to send a message out to all devices on that are attached to this switch, it needs to broadcast, then it can do that. It can reach all of the destination devices that it needs to. This graphic here is showing you that switches can create what are called virtual LANs. You can actually go in and through the software on a switch you can identify that some ports are part of one segment and the other ports are part of a different network segment. And so those are referred to then as virtual LANs, because they're not physically separate switches. It's the same switch, but through software we've gone in and we virtually have created these LANs. And it does isolate the traffic, which means that the devices that are hooked up to the switch port Bs that you see are there on the left, they can all communicate with each other. And the devices on the right that are connected to switch ports As, they can all connect and communicate with each other. But when a broadcast message is sent, the A devices, their broadcast won't be received by the Bs, and vice versa. Any B connected device would not be able to broadcast information to the A network. So they're essentially isolated from each other. They are segmented from each other, which is one of the reasons that we do this within a network. One of the reasons we segment a network is to reduce broadcast traffic. So this graphic then still is showing virtual LANs. You can see that there's two switches though now, and the right side of the first switch, the left-hand switch there, has several ports assigned to A, and then the right-hand switch also has several ports assigned to A. And so again, all of the devices that are connected to what are virtually assigned as being part of segment A or subnet A, network A, however you want to refer to it, they can all communicate with each other. And then in this example with the two separate switches, then there's also additional virtual LANs B and C that have been created, and they're totally separate from the A network there. Now when we're talking about switches, you want to always remember that switches by their original design are layer 2 devices, meaning they can read the data link layer information, the MAC addresses. That's what makes them a switch. A hub can't do that. All a hub is just a repeater. It just simply regenerates and retimes the signals that it's receiving, and it doesn't make any intelligent decisions as far as what ports it needs to send the information out of. That's why a hub sends it out, receives a message and sends it out of all ports. A switch, however, it can read the incoming message and say, oh, here's where the destination MAC is, and it's attached to this port over here. I'll only send that message out of that particular port. So that's what makes it a layer 2 device, the fact that the switch is actually reading the MAC addresses, the destination MAC addresses, and then determining which port that MAC address is attached to. So, regardless of the number of switches in the VLAN environment, the virtual LAN still require the use of an external standalone router to route the traffic from one VLAN to another. So remember in the previous graphics I was telling you how A and B, they're isolated from each other, even though their switch ports are ports that are connected physically to the same switch. through the VLANing process, they are segmented, they're separated from each other. So in order for B to talk to A, or A to talk to B, or in this case A to C and D, and you know, all of these networks to talk to each other, we need to have a router. And so that's what this graphic is showing you, is that there's one switch port from A, one switch port from B, one switch port from C, and one switch port from D that are all connected to 4 different interfaces on the router there in the top middle. And so it's the job of the router to be able to forward then the information from one segment, one virtual LAN, to another virtual LAN. So again, that's in a layer 2 switching environment. With a layer 3 switch, you now have network layer or routing capabilities built into the switch itself. So that's why these switches are much more expensive than your standard layer 2 switches. They're actually capable of forwarding the traffic between their own virtual LANs and other virtual LANs that exist out there, because they use the network layer routing capabilities, and they're able to build routing tables and just, you know, anything like a standard layer 3 device or router would be capable of doing. So these layer 3 switches can actually take the information from the various virtual LANs and forward it to the appropriate destinations without the need for an external router. This provides a performance boost by operating at both layers 2 and 3. And as I said, it adds to the cost of the device as well.